And today talks is delivered by Glinyanaya and devoted to multiple integrals with respect to point measures which arise in the Arratia flow. Please, Katerina.
Thank you. So I will share my screen now, and this full screen. Oh, okay. So my talk is about multiple integrals with respect to point measure that corresponds to the Arratia flow, and I will start from the statement of the problem that we will consider today. Today I will consider the following question. So I will have a locally finite point process. So later I will specify it as a point process that is associated to Arratia flow. And the question is about how we can write the random variable that is measurable with respect to this point process, to such a sigma field, as a series of orthogonal components of such form. So of the form of integral operators with respect to a point process mu. So this is the main problem of our interest, and here the first step for solution of such a problem is to find the orthogonalization of the set of multiple integrals with respect to a point process. So, and today this is the question of my interest. So how I can find the orthogonalization of such set of integrals. I will consider functions of integrand to be symmetric and from space L2. So let's see what we can do now. Okay, so as I said, the case of interest is the point measure that is associated to the Arratia flow. So I recall that Arratia flow consists of Brownian motions that starts from every point of the line and move independently up to their meeting. After they meet, they coalesce and move like one particle. So, and the point measure we can define as follows. And this is locally finite measure because we know that only a finite number of particles are located in a finite subset for every positive time t. So this measure is of our interest, as I said, and I will illustrate today's talk with known result about orthogonal decomposition for a Poisson point process. So this is the such a point process that has independent values on non-intersected subsets of real line, and the value of a number of points in a subset delta has Poisson distribution of such form. So for a Poisson process, the result of orthogonal decomposition of measurable random variable is known. But to talk about it, let us recall some powers of a point process. So I just want to be sure that we are talking about the same objects. So for point process of a such form, so if I consider just sum of delta measures at some points, I can define so-called factorial measure mu in power mu m. I will denote it as follows. This is just sum over all non-equal indices of delta measures at such m points. And we should know that this definition not equal to usual power of measure mu, because for in such notation of measure mu as sum of delta measures, we can write the usual power of measures like sum over all indices of the same and the same summations. So this is the difference between factorial powers of measures and usual. So I talked about such powers and its connection previous time. So maybe I will not pay attention today for it. And what is very important for characterization of a point process is their so-called factorial moment densities. So if I define the factorial powers of measure mu, I can define corresponding factorial moments as follows. So this is just an expectation of factorial power of measure mu. And if such a factorial moment has density with respect to Lebesgue measure, then we will call this densities as endpoint density for a point process mu. And it turns out that this endpoint density can characterize a point process. So they are very important, and we know them for example, for
Katya,
yes.
Katya, can we ask you? Can we justify your statement? Characterize? Can we say that in most common cases we can reconstruct the distribution of the point processes from these point densities?
Reconstruct. I'm not sure that I know the procedure of reconstruction, but under some condition for moments of a point process, if we know that the set of all n point density that is again, the same for a two-point process. We can say that this two-point process have the same distribution. Yes, of course.
Okay, thank you.
Yeah, but how to write some? Yes.
Maybe about how to write, maybe we can consider Laplace functional from
Yes.
measure, and Laplace functional can be transferred into the series of multiple integrals, and expectation is exactly the integrals which we respect to factorial measures.
Yes, yeah, yeah, sure.
Okay.
Yes. For example, for the Poisson point process, due to its dependency on non-intersected subsets, one can get that nth factorial measure is equal to usual power of intensity measure. So if we consider Lebesgue intensity measure, then factorial measure is equal to this power. So the density is equal to 1. And for the case of the Arratia point process, the endpoint densities was obtained by Tribe and Zaboronsky in terms of so-called Pfaffian. So we can understand in this case Pfaffian of antisymmetric matrix as a square root of its determinant. So in this case, we have here kernels that form antisymmetric matrix. So we can just say that this is square root of determinant of matrix K. So here we can see that maybe this is not so easy to write the precise formula for endpoint density test, but later I will use the formula for two-point densities, and we will see how how this density test can affect on properties of space of multiple integrals. Okay, so now I would like to say some words about known result about a Poisson process. So in order to find the orthogonal decomposition of a measurable random variable, we can define orthogonal integrals. So and they are defined as follows. So we will define a multiple integrals again for symmetric function f as follows. So here we will sum with some coefficients integrals with respect to factorial powers of a point process times usual power of Lebesgue measure lambda. And in such a notation, this is just an integral of f with respect to such measure. To be more precise, I give here example for the second integral, and we can see how we need to orthogonalize two-dimensional integral of a function f with respect to second factorial power of point process eta. So we need to subtract such an integral and add integral with respect to the back measure. So this is some procedure of orthogonalization, and for a Poisson process it can be easily done. And the statement about orthogonalization of such integrals is represented here. So we can see that for non-equal orders of an integrals, we will have zero scalar product in L2. And using these orthogonal integrals, the Gauss expansion of functional of point process is known, so we can write it as convergent in L2 series of multiple integrals, and kernels are given in terms of such expectation of analog of derivatives of measures. This is derivative of a point measure. So here, so this is known result for a Poisson process, and I would like to notice here that in this case the solution is simple, because we have independent values for non-intersected subsets, and this is the main feature of the process that allows to obtain such decomposition.
May I ask a very short question? When you say about orthogonality, you mean only that expectation is zero, not you don't have independence in general, right?
Here, when I talk about orthogonality here, I mean this property.
Mm-hmm.
So if I have integrals of different order, they have zero scalar product, and for each of such integrals the expectation is zero. So this is usual orthogonality in L2.
Vitaly, in Gaussian case, there are very interesting relationship when we can conclude for multiple integrals from orthogonality of these integrals and its powers, we can conclude independence. Maybe for Poissonian, but I'm not sure. But in general, we cannot expect this.
I just asked because I know this relationship for Gaussian, because it is well known fact. But I thought that probably it is also true for Poissonian, because actually you have a lot of independence in Poissonian in Poisson.
Yes, I think that Engelbert, when considered with his student Lapen, in his article in Annals of Probability, considered some statement related to this, devoted to Gauss expansion with respect to special martingales. Yeah.
Mm-hmm. Okay, thank you.
Okay, and here for illustration some example that for if I consider a functional of point process of the following form, so I just consider exponent into the power minus here integral of some function of a positive function v with respect to a measure nu. Then for such functional, just this is not hard to calculate this derivatives. I would like to show this. So this is just the difference between, oh, here, I'm sorry, here not mu.new, so I just add one point at point x, x, and take difference. So it can be easily calculated, this relationship, this formula for the derivative, and the orthogonal decomposition for such functional has the following form. So we just have here such a series. Okay. And now let us come back to the case of the point process of the Arratia flow. And here I would like to recall the statement that how we can define the multiple integrals of square integrable symmetric function. So if I consider such operator, then it defines a continuous operator from the space of symmetrical functional functions to the space of square integrable random variables. And here the main property that allows us to say that this is a continuous operator is such uniform bound on uniform with respect to x, I mean, for n point density for the Arratia flow. So we have such a bound, and we can say that this operator is continuous. Okay. So if now I can properly define such multiple integrals, I would like to represent how I can represent L2 norms of such multiple integrals. And here the statement about such representation. And in today's talk, I will denote by such symbol with index n the inner product of the inner product in L2 on the 0 n to power 0, 1 into the power n. And using this notation, I can write the second moment of n-dimensional integral with respect to measure mu as following scalar product of f with action of linear operator k n on a function f. And linear operator k is given by the following formula. So I will show some step how we can get this result. This is just simple combinatorical consideration that we can write the square of integral of function f with respect to factorial moment as such product. And what I need to rewrite this sums as sum with respect to non-equal indices here. in order to obtain later the integral with respect to endpoint densities. So if I have such equality, then I write just the expectation here and here, and then this expectation of such sum is just the integral with respect to such functions, like we saw in the statements in the statement of the theorem here. So this is just this. Okay. So let us write the precise formulas for these operators, because later I will use them. So for example, in order to calculate the second moment of one-dimensional integral, I need the operator k from L2, 0, 1 to itself of the following form. And here I will here notice that okay, and for the two-dimensional integral, I have the operator from L2 on second of two-dimensional space of the following form. And here now I will note the main difference between these operators. Here we have some integral operator plus some multiplication operator, and here multiplication on non-zero value. But in the case of the for two-dimensional case, we have here also we have some integral operators with continuous kernels. They are fine. But we have here multiplication on some function that is 0 on diagonal. So this is a property of n-point densities of a point process, that if we have equal value of coordinates, then it is equal to 0. So this is not very good for our case when we will try to find some. Okay, we will see it when it is not so good. Okay, so this is how I can find the norms of the second moments of multiple integrals. And next, what I will use today is how I can find the so we can imagine that this is a scalar product for multiple integrals with different order. So for such formula, I assume that I have m less than n, and I consider symmetric functions f and g. And then I can write the scalar product of multiple integrals, again using the scalar product of function f and some operators that x on function g, or like, so this is just formattation, because I will write precise formula for adjoint operator k also, but maybe it's not important for now, but it's interesting to write the precise formulas for them. So here the linear operator k with indexes m and n acts now from L2 of dimension m into L2 of dimension n, and this is given now by this formula. So now I take function g from lower dimension and I get the function of dimension n. So this is the formula for such operator, and here the formula, and summons we have here such integral operators. So to be more to understand the action of such operators, we can write them for example for case 2 and 1. So we can see that if I have function g of one dimension, then I get by such formula function in 2 dimensions, and it will be symmetric because endpoint densities are symmetric functions. So this is just for illustration how we can understand these formulas. Okay, so now in order to start procedure of orthogonalization of multiple integrals, we start step by step, and let us consider the subspace of one-dimensional integrals of the following form. I'm sorry, here maybe I should write not R but 0, 1. And in order to find the orthogonal decomposition of two-dimensional integrals on space of one-dimensional integrals, I will use projections, and to this I need to know that this space is closed. So let us see how we can get that this one-dimensional integrals form a closed subset of two-dimensional of random variables in this space. So to see this, so this is the proof, and if we assume that we have a sequence of if we have convergent sequence of random variables of the form of integrals to some random variables psi 0, then we need to show that this psi 0 can be represented as integral of some function with respect to measure of mu. So to do this, what we need to show, we need to prove that we can find such a constancy that satisfies such inequality. So in other words, this means that the operator of second moment is satisfy such a property. So we can find inverse operators. So let's do this. So I recall that the second moment of one-dimensional integral I can write in such a form. So K is operator of following form. This is integral operator plus multiplication by a constant, And to see this property, it is enough to show that this operator is invertible. So we have a good case when we have operator of a form identity plus some integral operator with kernel row here. And to prove invertibility, we need to just to check now that this operator A of such that is integral operator with the kernel row satisfies such inequality, that norm is less than some constant. So this is where the property of this 2-point densities play role, because we see now that it is important to have a precise formula for this endpoint density and to understand how we can estimate the norm of this operator. So I just write here the formula for 2-point densities. For 2-point density, it has some such a form, and also we know that it is bounded with such a constant. So here just a little calculus that one can do. I did not write here precise formulas here. We just need to estimate. So I take the estimation for a integral operator by square root of such integral of square of the kernel, and we just can check that such integral is less than 1 over p2, and it leads to bound that we need. So from this, if we come back, we will see that operator K is invertible now. So this operator is invertible. So we have that the space of one-dimensional integrals is a closed subset of random variables that are measurable with respect to point process. Okay, and from this statement, we can easily find the orthogonal projection of a two-dimensional integral to subspace of one-dimensional integral, because it's easier if we have a closed subset. Then we can find this such a function f. I add here sub g that gives us the orthogonal complement to two-dimensional integral. And here the formula for this function fg that we use in order to find orthogonal complement is given by this formula. So here we use this inverse operator K1 that we discussed on the previous lemma. So this invertibility of operator K1 is very important here, and this is just a precise formula. I just recall that I show you this operator K1 to adjoint that arose from the formula for scalar product of one-dimensional integral and two-dimensional integrals. So here this K adjoint now acts from L2 of 2 dimension into L2 of 1 dimension, and then we take here inverse operator of just norm of one-dimensional integral. So the proof is maybe quite easy, but I will show it here. So how we can find this function here? So I just want to minimize this L2 distance between one-dimensional integral and two-dimensional integral. So I know that such a function exists, and I can find it. So in order to minimize this distance in L2, I should minimize such form with respect to f. And this is given, one moment. I'm sorry, oh yes, so by this formula, yes, and here we have the just the formula for this projection of the following form. So this is how we can prove and find the projection of two-dimensional integrals on the space of one dimension. Okay, so this was just the first step in order how we can find orthogonal complement, and now in order to proceed follows to consider bigger dimensions. Now we will have here some problems. So if I want to continue these steps and find the projection of three-dimensional integrals onto the space of two-dimensional integral, it is not so easy, and maybe it's not impossible. It is not impossible because now if I consider two-dimensional integrals with respect to a measure mu, then it is that we cannot say that this is a closed subset in L2, and the reason why this is so, because we have here the operator of second moment that is not invertible now. Why is it so? This is because this part that I already told. So this one is a multiplication by some function that is 0 on diagonal. So now we cannot find invertible to this operator K2. And some examples that which can illustrate this is the follows. So if I consider such two-dimensional integral of the following form, so maybe that's not the same case, but this is an intuition how we can get from two-dimensional integral in the limit one-dimensional. So if I consider the such integral of the following form, and here function g is one periodic function, then such with such normalization, the integral of function g will converge to some constant. I'm sorry, here not g but f. Then function g will converge the integral 1 over n dx converges to some constant by law of large numbers that we discussed. I discussed this statements on the previous talks, and in the limit we will have one-dimensional integrals. So the next idea, okay, we cannot find the projection onto the space of two-dimensional integrals, so we need to find the projection into the space of all previous integrals. So for example, here, if I have a three-dimensional integral with respect to measure to factorial power of measure mu into the space of a following form, so I have some of one-dimensional and two-dimensional integrals. So this question leads to the question about invertibility of operator of the following operators. So let us denote operator A. We will denote the operator A from the direct sum of spaces of L201 plus L201 of dimension 2, and this operator A is given by the formula. This is this one. So here we have the operator of norms here, K1 and K2, and operators of scalar product of integrals of 1 and 2 dimensions. But again, we saw that this operator is not invertible here, and so for now I cannot find the projection of this three-dimensional integral on the previous one, just because I cannot find the invertible operator of here of this form of K2, and this is just because of its form that we discussed earlier. So maybe this is for now. This is what I have, and that's all for today. Thank you.
Okay, thank you very much for description of the problems where probability relationships are described via functional analysis and integral operators. And maybe somebody have questions or comments, please.
I have a short question, if I may. Katya, regarding your last result, I didn't understand the space of, I mean, the collection of the first order and second order integrals. Is that a closed subspace of L2 space, like in one-dimensional case, or you do not know at the moment?
For now, I do not know precise. So you said about this. So I assume that yes, that's right, but
because you said that you cannot compute the projection, and here just the question. My question is whether because you do not know whether it exists, or you know that it exists, but you cannot express that by the formulas which you actually need for the expression.
I do not know the answer for both questions, so I do not know if it is a closed subset, but I assume that it is.
It is related to the question in the functional analysis to the question of the closeness of the image of certain operator which contains integral terms. So at the moment, this is a problem in this approach.
I have a short question.
Okay.
Could you go back a significant number of slides?
Just a moment. Okay.
Yes.
More?
Yes, a little more. A bit. Here, maybe. Is this representation related to Pfeffians or some algebraic structure?
No, this is true for every point process.
And so, okay.
This,
I was wondering because
here, yes, this is just what is important to me that this properties of these operators, but I have here some specific endpoint densities, but this is this equality is true for
any.
any. This is true for any.
Yeah, I was wondering because I spent some time trying to get some convergence result for densities using these Pfeffian expressions, and I do not understand the algebra behind them, behind the permutation groups. Thank you.
Okay, some other questions, please. Let me also make some comment. As it can be seen from Katerina's talk, we have the case which is opposite in some sense to Poissonian measure, because of when we consider this Arratia point measure on the finite interval, we have dependence between values of such measure on the different sets. And to get independency, we have to do limit, some limit procedure, as Katya mentioned. For example, we can take periodic functions, then we get central limit theorem, not only for integral, but also for multiple integrals. And we have in the limit multiple integrals with respect to some Gaussian free field. From this point of view, it will be interesting to understand, at least on the large interval, we have the convergence to the orthogonal random variables, because in the limit they are orthogonal. And one can prove, as we did in our last paper, that these integrals converge simultaneously. So maybe they became to be almost orthogonal in the limit. So it is interesting to understand what happened with the orthogonalization, at least on the big intervals. I think that we can get some information from the statement that for a limiting object we have orthogonality. Okay. And also this is almost advertising. Next speaker will be me, and I will continue this topic, but from some other point of view. So for today we finish our work. Thanks everybody, and see you next week. Bye.